Hello everyone, myself Dr. Tazdarul Hassan Sayyed. I am an associate professor in the Department of Applied Geology, IIT ISM Dhanbad. In this module, I'm going to talk about how we measure hydraulic head in the field and how the measurements of hydraulic head and the differences in hydraulic head are used to measure important hydraulic and hydrologic properties of different aquifers. So in continuation, I would first like to say that hydraulic head is basically the sum of two components. One is the elevation head and another is the pressure head. But in the field, when we go to make measurements of hydraulic head, which is a very common practice, so what we look at, if we can very simplistically draw a diagram of a well or a groundwater well, so if this is my surface or the earth surface and this is a well which has been drilled, and here this is the level at which water stands in the well. This is my datum, which is the global mean sea level. So here what happens is that how do we calculate the hydraulic head of a particular well like this? So what we know is the elevation of the surface. So that means we know the elevation of the ground surface with respect to a particular datum. So then what people measure is basically what is known as depth to water table, which is DWT. That means from the surface, and we can put a tape inside and we see at what depth from the surface the water level in the well exists. So now if we go back to the definition, how we defined what a hydraulic head is, that the hydraulic head has two different components. One is the elevation head, which is defined by ZW, and the other is what? The other is the height of the fluid column or the water, where the water stands, and which we called it as the pressure head. So in order to calculate the hydraulic head, so the hydraulic head is basically ZW plus HP. Now the thing is, it is not possible sometimes to get the individual components. So what we do is, if we know the elevation of the surface and if we know the depth to water table measurements from the well, what we can do is we can calculate, say this is my hydraulic head H. So how we calculate H? H is basically given by ZS minus DWT. So here we can see that if I know the elevation of the surface and if I know the depth of the water in the well, we can subtract that, and finally what we get, as you can see from the diagram, is that we can get the H, or the value of H, which is basically the hydraulic head. So the thing is, this is one very common way to measure the hydraulic head of a particular area. So now what we do is, often in the field when we go, we take measurements. If we take measurements of hydraulic head from different places in an area, then if we can join those points or hydraulic heads over the entire area, and we can fit a plane surface on top of that, that is what we call as the water table. So the thing is, so what is the water table? So water table is nothing but the joining or a surface or a planar surface which consists of points which are basically the hydraulic head at different points in the area. Now what happens is that, so we can, this is a very common term which we see to define the status of groundwater. So often we see that during the summer months the water table goes down. So and during the monsoon months the water table goes up. So what it says is that when the water is being extracted at a rate more than how much of water is infiltrating into the ground, what happens is that the water table goes down. Water table is basically an imaginary surface. So what happens is it goes down, and when during the monsoons, when there is a lot of rainfall, so what happens is that the input into the system is more than the output. That means more than the groundwater that is extracted out of the system. Then what happens? The water table rises. So here basically water table defines the hydraulic head of the area in a very simplistic terms, and it is not a constant surface. That means it is not time invariant, it varies in time. And what it is dependent upon? It depends upon how much of water is being drawn out and how much of water is coming into the system. Okay, now this is what is basically a static water level. Now the question is that what happens when I pump out water from a well? So if I take a situation like this, a similar diagram in which I am showing that this is my surface, this is the well in which there is water, and standing here, so if this is the water in the well, and this is the representation of my water table. Because, so how did I draw the water table? So if I would have supposedly measured groundwater hydraulic head in all these portions, and if I join those points with a line which is basically representing a plane, I get what is known as the water table. So if this is the water table, which is generally represented by an inverted triangle, so this is what I call it as a static level. Okay, now the question is, what happens when I pump out water out of it? Now let's say if I am pumping out some fixed volume of water Q out of this well. Now then what happens to the water table? So what happens actually is something like this. So we see, say for example, this is time t0. This is the behavior or the nature of the water table at time t0 when there is no pumping taking place. Now supposedly at time t1, after time t1 I started pumping out water. Now what would be, how is the water table going to behave is basically it is going to appear something like this. So what happens is that we see that this is the water table, this is the status at the water table at time t1 after pumping has started. So what we can see is that there is a depression forming near the well, and as you move away from the well from which pumping is taking place, we see that the water level actually is becomes very similar to the static level or the before pumping levels. Now if I represent the hydraulic head here, that is before the pumping has started, as H0, and after the pumping has started, say after the pumping has started, with the water level becomes like this, say HT. So what happens is, see the difference in these two water table due to pumping, which is represented by H0 minus HT. There is a specific term used to quantify this, which is known as a drawdown. So what we see here is that the change in the level of water in a well is basically from before pumping and after pumping is known as a drawdown. Now sometimes what happens is that the well from which pumping is taking place is different from where people are measuring the well. So here we can see that if, for example, I put another well here, say I have another well, but here I am not pumping the water, I am actually measuring the water table. So here also I will see that before pumping the water level was at H0, but it is somewhat away from the pumping well. So as we can see, because the depression actually fades away as you move away from the pumping well, what happens is that you see here, let's say, let us call this the water level at this point, say water is standing here, as say HT2. Okay, so now what is the drawdown here in this well? The drawdown is H0 minus HT. And what is the drawdown in this observation well? This is basically H0 minus HT2. So This is a drawdown value, this is another value of drawdown, but as we can see that the H0 minus HT, this drawdown H0 minus HT is greater than H0 minus HT2, as you can see here. Why? Because the cone or sort of the depression that takes place is becoming lesser and lesser. So what I'm trying to say here is that the impact of pumping on the water table basically fades away radially as you move away from the pumping well. Now imagine this is a situation where I'm drawing a cross section of the land surface. Now water is basically, now imagine the whole thing if I can extrapolate into a three-dimensional space. So now what happens, we can see that instead of this two direction from which water is, there is this depression, imagine this happening in three dimension. So what we form here is sort of a cone. If you can think of a funnel, it's like a funnel which is basically all depressing towards a common center. So what happens is that's what we call as a cone of depression. So the movement of water, as we can see, if we talk about a three-dimensional space, the water is basically moving like the spokes of a cycle wheel. As we can see that the spokes, what happens is from the outside, it is merging towards a common center. So if we can draw the flow lines of water, you will see that it is like the spokes of a wheel of a cycle. So what happens is we see that there is a cone of depression which forms because of pumping, and this is the difference that we see is known as the drawdown that is taking place because of the water, okay, because of the extraction of water. Now what is the importance? Now this drawdown is something very, very important, and it helps us in determining some of the key hydraulic properties of an aquifer. Okay, which is, I'm going to discuss now that how these measurements of drawdown are used to get these, very important hydrologic or hydraulic properties of an aquifer. So the measurements of drawdown is very, very crucial for determining some of the key aquifer properties. Okay, so what are these properties? For example, one is storativity, which is defined by capital S, and another is transmissivity, which is given by capital T. So the storativity is basically, it's a property of the aquifer. It basically says how much of water will be released from a unit area of aquifer if there is a unit drop in hydraulic head. And the transmissivity is a property of the aquifer which basically shows how the water is flowing from one side to the other. And if you remember Darcy's equation, this is given by K times B. K is the hydraulic conductivity, and hydraulic conductivity, and B is the saturated thickness of the aquifer. So basically it is the thickness of the aquifer. So here basically this is a term, hydraulic conductivity, which describes the ease with which water flows from one part to the other. And because remember, we are dealing with a saturated porous matrix in which water is stored within the pores, and the flow is also along the pores, or because it depends on the interconnectivity of the pores and other different parameters. So these are two key properties which are very much required for any kind of hydrogeologic investigation. Now the question is, how is the hydraulic head measurements, or the differences in the hydraulic head measurements, which we define as drawdown, is used to get these two, or get the estimates of these two properties? Now how it is done is basically it's a field experiment which is known as a pumping test, or sometimes it's also known as an aquifer test. Okay, very simply put, what happens is that we go to the field, and then we have a well in which a controlled pumping takes place. So in a controlled manner, at a fixed volume, pumping of water takes place, and what is looked at is the response of the water table with respect to this pumping. So for example, I have a well, there is a finite volume of water is being pumped out, which is Q. But what are the measurements? The measurements are basically the measurements of drawdown, either with time or with distance. So for example, if I have one pumping well and another observation well, what is done is that in this observation well, how much the drawdown is changing with time, that is measured. And in some cases what we have is one pumping well and we have several observation wells, so that are located at finite distances from the pumping well. So what happens is that the drawdown is measured at all these different wells at the very same time. So what we'll see is that how these measurements of drawdown, which is varying either with time or with distance, is used to get these important properties. Okay? And as I said, remember, in the field, there is everything is happening in a three-dimensional space. Okay, so how are these properties obtained by using the measurements of drawdown? Is that first try to understand, without going into the details, what is the equation of groundwater flow in case of in radial coordinates. Okay, so if we see that the groundwater flow equation goes like this. It is d2h dr square plus 1 by r dh dr equals to s by t dh dt. Okay, and this is the equation of groundwater flow in radial coordinates, because as I said, the flow of groundwater, if you see, is basically like the spokes of a wheel, so better represented in a radial coordinate. Now, what is the solution? So the solution to this was proposed by C.V. Thies, and the solution basically says that the solution to this equation is something like this, that H0 minus H, which is basically the drawdown, we have been calculating. H0 is the hydraulic head before pumping, H is the hydraulic head after pumping for some time. This is given by Q by 4 pi T, and there is an integral to infinity minus u by u du. Okay, so here this is the equation of the solution, the Thies that the solution proposed. Okay, now this part of this integral part of this equation, okay, is basically represented by W u, which is the also known as a well function. Okay, now what is u? U is given by r squared by s for t, where t is the transmissivity and small t is basically the time, s is the storativity, r square is the radius of the well or observation well where it is located. So okay, so the well function Wu is basically, if we can split it out, it's basically an infinite series. Okay, so Wu is basically goes like this: minus 0.577216 minus natural log of u plus u minus u squared by 2.2 factorial plus u cubed by 3.3 factorial dot dot dot. So it's like an infinite series. Okay, so if this w is a function of u, as we can see here, is represented here. So now what we can do is we can rewrite this equation, which was the the Thies solution, the Thies formula. What it is basically, if we remove the integral and just write the W or represented by the well function. So here I can rewrite this equation like this: H0 minus H is equals to Q by 4 pi, and this is 4 pi T. So instead of the integral part, I removed the integral part and I wrote Wu. Okay, just to reiterate once again what this equation, this is known as the Thies formula. Okay, so this is known as THEIS, Thies formula. So what it says is that basically the drawdown is given by Q. What is Q? Q is the volume of water that is pumped, and please remember that this is a constant volume of water that is pumped in time. And T again is the transmissivity, and then basically WU is the well function. Okay. So now when we have the well function W, which is represented by WU, and if we plot the well function versus the inverse of U, this is known as in a fully logarithmic paper. That means both these two values are represented in log scale. What is the curve that is formed is basically, if I plot WU, this is 1 by U, this looks like this. You know, the shape of the curve is representing almost like the depression of a water table, and this curve is a standard curve which is found in any book of hydrogeology. This is known as a reverse type curve. So this is a standard curve, and this is the curve which is used for the graphical solution of the Thies equation or the Thies formula. Now, how is this curve used in this graphical solution? Is that what we measure in the field. Remember, when we are measuring in the field, we are measuring drawdown only. Okay. So now, in this case, what happens is, what the solution was given by Thies is for the graphical solution of this is that we measure in the field drawdown and with time. Okay, so it's in a very similar manner we are measuring H0 minus H and the time is in the x-axis. Again, these two variables are also plotted in the logarithmic scale. Okay. So if this is done, now going back from the equation, the original Thies equation, which we said is H0 minus H equals to Q by 4 pi T WU. And here I can rearrange this equation to get the value of T, which is the transmissivity, which goes like this. If I just simply rearrange it, as we can see, 4 pi by H0 minus H times WU. Okay, and once I get the value of transmissivity, I can get the value of storativity. How? Because we know value U is equal to R square S by 4 T, which is in time. So what we can do is we can rearrange this equation and we can write as S equals to 4 T U T by R square. Okay, so here what is the solution to this? So first of all, let's remember that the type curve is a curve which is basically plotting WU times Y versus 1 by U. Both are in log scale. Similarly, we make another figure or another plot in which we are plotting the drawdown with time, and again these are also in a log scale. Okay, and what happens is that you get some points like this. Okay, which is basically looking like this. So what does the graphical solution say? The graphical solution is basically saying that we overlay the type curve on top of the drawdown curve. Now, how do we overlay? We have to be very careful about two things. One is that this curve is falling or more or less matching with the points of drawdown versus time. And the most important thing is that the axis of these two curves are parallel. Okay, so keeping these two axes of the curves parallel, we have to see that we're trying to match these two curves. Okay, so once we have done that, then what we usually do is we take a pivotal point or a match point, and what is known as the match point. So what is the match point? Match point is basically where W, the value of function of WU is equal to 1, and also the value of U by U is also equals to 1. Okay, so here if this is the match point, then what we try to do is at this particular 2 points we try to find out what is the value of H0 minus H, that is the drawdown, at this match point, and also what is the value of t at this particular match point. Okay, so once we get the value of h0 minus h, which is the drawdown, and that of the time, we can put these values in the equation. How? If we look back into the transmissivity equation, what we know is Q, because we know that that's a fixed discharge, volume of discharge. H0 by W, U value you know. Why? Because in the match point, the value of W is equals to 1. And for the corresponding value of the drawdown at the point W equals to 1, we know by matching these two curves. So what happens? So I have the value of H0 minus H, I get by matching the curve. W equals to 1, I know. Q is a fixed value, I know. So I can get the value of transmissivity. Now, once we get the value of transmissivity, we can put it in this equation where we can estimate the value of storativity. Now, how do we know? We know the value of T from the previous equation. We know the value of R square. Why? Because we know what is the distance of the well from the pumping well. And we know the value of U, because 1 by U equals to 1. And the value of T, how did we obtain? The value of T we obtained from the match point and by overlaying one of the two curves. Okay, so here we can see that if I can get the reverse type curve, which is a standard curve, and we can plot the drawdown versus the time, then we can match these two, and then finally we get the values to get an estimate of transmissivity and storativity. Okay, so this is what is known as the Thies solution, or the Thies graphical solution. Okay, later on, what C.E. Jacob later on had simplified this method a little bit. Okay, under the assumption that if he saw that if the value of U, which is defined here, is less than 0.05, then he saw that the higher order terms of the well function can be ignored. Okay, so what he saw was that for lower values of T, or if the values of U is very, very small, how can a value of U be small? Number one is that if you look at this equation, if the observation well is very close by because of the radius, if the radius is small, then the value of U can be small. Or if the value of T, or the time over which measurements are taking place, is very, very long. So if observations are made, so the two conditions are required for the Jacob method is that, one, the observation has to be either very close to the pumping well, or the observation has to be taken after a very, very long time period. Okay, so now if we look at this equation, the WU function, so here the WU function, which was an infinite series, now the Jacob actually said that it can be ignoring the higher order terms of the equation. So what he suggested was that basically the WU can be represented by the shortened form of WL function is basically this. Okay, so now if we consider the equation, what he found out, or what he suggested, was that the drawdown H0 minus H by the Jacob method is equals to 2.303 Q by 4 pi T, and then basically says log 2.25 T by R square. Okay, so this is the modified Thies equation, and in which we can see that this is the equation of a straight line. So in this method, what happens is that here again we measure this thing, measure the drawdown, which is given by H0 minus H in time. But the only difference is that the H0 here is represented in an arithmetic scale, and T is given in a log scale. Okay, so what happens is that generally the plot of the points looks like this. Okay, now what happens is that in the graphical method, this is, remember, this is the drawdown is 0 here. So what happens is that if we fit a line which basically passes through these points, and if we can extend it further towards the 0 drawdown level, wherever this meets the zero drawdown axis, this point, the corresponding value of t is known as T0. Okay, so here what we try to obtain here is that the value of T0 is very, very important. So this is one parameter we get from the curve. Another is the slope of this line, which is basically delta H0 minus H. Okay, now how do we use this in the equation, modified equation? Here we say that the value of transmissivity is equals to 2.303 Q divided by 4 pi delta H0 minus H. And what is this? This is basically the slope of the line, and here we can obtain the slope of the line from the curve. And then, once we have the value of the value of transmissivity, we can obtain the value of storativity by using the value of T0. Basically, it is given by 2.25 T0 divided by R square. So here in this equation, as we can see, that we have obtained the value of transmissivity, and the T0 is obtained from the curve, which is basically an extension of the line which represents the points of the drawdown extended towards the zero drawdown axis. Remember, this is the axis of zero drawdown, and for the corresponding value of time is known as T0. So we can get two values from these two from this curve. One is the slope of the line and another is the value of T0, and we can put in this equation in order to get the values of storativity as well as transmissivity. So a summary of the module, as we saw that the difference in the heads or the hydraulic head before pumping and after pumping is basically known as a drawdown. And we can see here that there is a characteristic curve that develops, and in the case of where the drawdown is taking place, and we can see that the drawdown is maximum towards the well where the pumping is taking place, and it starts to fade away in order to form a cone of depression. And this measurements of drawdown, which we can do in the field over time or over space, can be used in the Thies equation for solving the Thies equation in a graphical method. And we saw two different cases. One is the Thies method, in which we need the reverse type curve, which we fit on the drawdown measurements over time. And another one is the modified method, which is the Jacob-Thies method, sometimes it is called, in which we use a linear equation, we change it or modify it into a linear form, and we can plot it in a graph, the drawdown versus time, and we can find out the values of storativity and transmissivity. Thank you very much for your kind attention. Thank you all.